In space missions, it is significant that satellites or spacecraft are usually placed at stable points in a binary star system, and these points are called Lagrange points. The existence of these points helped the spacecraft to save a large amount of energy, and normally we work out the location of these points using the force equations. However, in this video, we're going to explain the existence of these points using the idea of an energy diagram. As we know, a star has a really large mass, usually around 10 to the power of 25 kilograms. This large mass causes them to be strongly attractive. The heavier they are, the stronger their ability to pull masses towards them. We can illustrate it by using a simple graph. With a larger mass, the shape of their slope will tend to be even steeper. However, because the two stars are rotating, the case can be more complicated than we thought. But before we consider the stars, let's first imagine a simple scenario, a ball rotating on a plate. When we stand beside the plate, it is easier to understand why there's only friction in the system. The ball is rotating and force is applied to the ball to change direction in every moment. On the other hand, something could appear weird when we change our perspective to understand the system. If we stand on a plate and rotate with it, the ball will be stationary. But wait, didn't we just mention that there will be a friction in the system? As we know from our great ancestor Isaac Newton, if a body is at rest or moving at a constant speed in a straight line, it will remain unless it is acted on by a force. In order to fit this law, we have come up with a force to balance the friction. And in the rotating star system, this force also exists in order to balance the attractive force in a rotating wheel. The effect of this force on the graph will be a hill. Hence, we found the factors that are contributing to the system. Now, if we combine these two diagrams together, and because these factors happen together, we have found the physical picture of this binary rotating system. It must still be difficult to tell the 5 points from the graph, but it will be easier to see after understanding the equilibrium. Assume that we're putting a small ball on the system and imagine the whole graph is a part of the mountain. If you try to put the ball on the slope, it will tend to roll down and finally stop at the lowest potential energy point, like a valley. However, if we put the ball right on the peak and to make it balanced, it will still be in equilibrium and stay still. Now, finally looking back to the picture of the binary star system, we can see that there are 5 significant peak or valley points on the graph, which are the 5 Lagrange points. Even though these points are not perfectly stable equilibrium points, with the help of some special orbits around the point, the properties of Lagrange points can help spacecraft to save a lot